Welcome back to week 5 of the ma135 ma160 calculus. My name is Götz Pfeiffer and this video is about reduction. Here we're going to use the integration by parts to obtain rules that might have to be applied a couple of times in order to eventually solve an integral. So we start with the observation that sometimes it's necessary to apply the integration by parts twice. In this example, we're looking at the integral over x squared times cosine x dx. So, if following the general strategy, choosing u and dv in such a way that the integral on the right hand side of the integration by parts rule becomes simpler, I would take u to be x squared and then dv is the cosine of x dx. From that we obtain du as 2x dx and v as an antiderivative of the cosine of x is sine of x. So by the integration by parts rule, the original integral, which we have now described as an integral of the form u times dv, this integral is equal to the product uv minus the integral over v du, where v is sine x and du is 2x dx. So this is x squared sine x minus the integral over sine x times 2x dx. And that's again the integral of sine x times 2x, or x times sine x, isn't in the table, isn't straightforward. So we apply integration by parts again, or we remember that we've done this example before by integration by parts, to find that this integral over x times sine x dx is minus x cosine x plus sine x plus c. And then so we have this extra factor 2 in here, and then taking everything together we get that the integral in question, the integral over x squared times cosine x dx, is x squared sine x minus 2 times minus x cosine x plus sine x plus c, which you can, if you want, rewrite as x squared minus 2 times sine x plus 2x cosine x plus c. The point being here that one mustn't give up if integration by parts applied once doesn't yield a result immediately. Sometimes it's worth to persevere and try it again. Sometimes when you apply it twice, you might feel like running in circles, but you're not, as in this example, which is about the integral over e to the x times sine x dx, the product of the exponential function and sine x. So here, if we choose u to be the e to the x part and dv to be sine x dx, then we find that du is e to the x dx. That's the derivative of the exponential function is the exponential function, and v is an antiderivative of sine x, that's minus the cosine x, and integration by parts then allows us to express this integral as the product of u and v, that's e to the x and minus cosine x, minus e to the x times cosine x, minus the integral over v du, and taking the minus sign out, this becomes plus the integral over e to the x cosine x dx. Not much is gained here really. We've replaced the integral over e to the x sine x dx by the integral over e to the x cosine x dx. But yeah, let's keep going. Let's apply integration by parts a second time. So following a similar strategy as before, taking u to be e to the x and dv now to be the cosine x dx. Du becomes e to the x dx, and v is sine of x. And so using integration by parts, we can write the integral over e to the x cosine x dx as e to the x sine x, that's the product of u and v, minus the integral over v du, that's the integral over e to the x sine x dx. And that brings us back to where we started, right? There we are. With our old integral e to the x sine x dx. So the integral over e to the x times cosine x dx, now we find is e to the x times sine x minus our original integral I. That didn't lead anywhere, did it? Well, let's see. If we take things together now, we find that the original integral I we have expressed as minus e to the x cosine x plus something that we've now found to be e to the x sine x minus I. So our integral I is equal to minus e to the x cosine x plus e to the x sine x minus I. If we bring this I to the other side, we can actually solve this equation for I. We get 2 capital I if we move this one over, equal to e to the x sine x minus cosine x. So this gives that our integral is in fact half of e to the x sine x minus cosine x plus c. Solving this equation in terms of I for I. So that can happen. And yeah, in this sense, applying integration by parts can lead to so-called reduction formulas, which don't ultimately express an integral in terms of formulas, but they do express integrals in terms of other integrals which are simpler, so somehow smaller in order of magnitude. Sometimes, typically, integrals involving powers of things being expressed in terms of integrals involving smaller powers. So here's an example that's concerned with the with powers of the sine function. Sine x to the power n, the integral over sine x to the power n dx. Here it's worth recalling that this notation, sine to some power, really means sine x raised into that power, and sine x multiplied with itself 3 times here. Sine cubed of x is the cube of sine x. That's what the notation stands for. And in this context, it's also worth remembering this basic trigonometric formula, the equation of the circle, that the sine x squared plus cosine x squared is 1. We might use this. So the example of the reduction formula here is about the nth power of sine x, the integral over sine x to the n dx, being described as minus 1 over n cosine x sine to the n minus 1 of x plus n minus 1 over n times the integral over sine to the n minus 2 of x dx for n greater or equal to. So, as I said earlier, the purpose of this reduction formula is to express an integral that involves a power, the nth power here of sine of x, as a formula that involves another integral, but that integral has a smaller, namely n minus 2 power of sine of x in it. And so the reduction formula can be used to work out the original integral in a couple of steps. We'll see how this works after establishing the formula here. So how does this work? Well, we're going to apply integration by parts. So we need to identify our u and our dv, and for that purpose we rewrite the nth power of sine x as a product sine x and the n minus 1 power of sine x. Then in there we choose the n minus 1 power of sine x to be the u, and for the dv we take sine x dx. That's a distribution of roles between u and dv that we can work with, because from dv being sine x dx we can work out v as an antiderivative of the sine x, and we can apply the power rule to find the derivative of u, can we not? And find that du is n minus 1 times the n minus 2 power of sine x times the derivative of sine x, which is cosine x dx, and v, of course, is an antiderivative of sine x is minus cosine x. Now with these in place, we can apply integration by parts and express our integral in as the product of u and v, that's the n minus 1 power of sine x times minus the cosine x. And from this we subtract the integral over v du, where v is the minus cosine x and du now is n minus 1 times sine to the n minus 2 x cosine x dx. Okay, so what? We want to simplify this, so we take the minus signs in front, and we take this minus sign out and cancel it with that minus sign. We bring the two factors cosine x together to give us a cosine squared. And so this expression simplifies to minus cosine x sine to the n minus 1x plus n minus 1 times, taking the n minus 1 factor out of the integral, cosine squared of x times sine n to the minus 2x dx. Now it might be a good idea to apply this trigonometric equation sine squared plus cosine squared is 1, replacing the cosine here, the cosine squared, with 1 minus sine squared, so that we have only sine x factors in this integral. Using this trigonometric equality, we can rewrite cosine squared x times sine to the n minus 2x as 1 minus sine squared x times the n minus 2 power of sine x, and multiplying things out, this becomes sine to the n minus 2x minus sine to the nx, right? N minus 2 plus 2 is n, so sine to the power n of x. And so we were actually interested in the integral over this expression. So the integral over cos squared x sine to the n minus 2x dx now is the integral over this here, which is a sum of multiples. So it's the integral over sine to the n minus 2x dx minus the integral over sine to the nx dx. And that was our original integral, that's the in. So we've now found that this integral is the integral over the n minus 2 power of the sine of x dx minus the original integral in. So, backing up, bringing everything together, we find that our integral in, now after applying integration by parts once, we arrived at this equation which involved an integral that we've now replaced by something else. We find that in is minus cosine x sine to the n minus 1x plus n minus 1 times the integral over sine to the power n minus 2x dx minus n minus 1 times the in integral. Okay, so we've somehow been there before. If we know, we can now bring these n minus 1 ins to the other side. So then we have n times in in total equal to the right hand side minus cosine x sine to the n minus 1x plus n minus 1 times the integral over sine to the n minus 1x dx. And that's after dividing by n. That's what the formula in the red box says here. The integral over the nth power of the sine function is something that involves then the integral over the n minus 2 power of the sine function. And that's a reduction formula. It reduces the integral of the nth power of something to an expression that is that involves a smaller power of your something on the right hand side. Doesn't solve the integral in one go, but it provides a way to compute it. So we can compute, we can apply it in some cases for some small values of n. Now here's the reduction formula again for you, and let's try to look at the case n equals 3. So the integral over the sine cubed of x dx. So there we're looking for I3, which we get by substituting 3 for n in the formula. So this is minus 1/3 of cosine x of sine squared of x plus 2/3 times the sine of x dx. And the integral of the sine of x dx, of course, we know. So that's then I3 calculated. Or, here's the case n equal to 4. The sine over the fourth power, the integral over the fourth power of sine x dx is obtained by substituting 4 for n in this formula, and we get minus 1/4 cosine x of sine to the 4 minus 1 is 3 sine of x, of course, so sine cubed of x plus 3/4 times the integral over sine squared x dx. Now here the integral over the sine squared is I2 is the n equals 2 case of this integral, which then needs to be evaluated separately. But I hope you see how this allows you in principle to calculate all integrals of this form of an nth power of the sine of x. Here's one more example of such a reduction formula. This doesn't go so much in circles, it's a bit more straightforward. The integral over x to the n e to the x dx. Here we separate the case n equals 0 from the rest. If n is 0, we're just looking at the integral over e to the x dx, which of course is e to the x itself plus c. If n is bigger than 0, we apply integration by parts, choosing u to be x to the n here, and dv to be e to the x dx, from which we get du as a derivative of x to the n, namely n times x to the n minus 1 dx, and v is an antiderivative of e to the x, which is e to the x itself. Substituting all of this into the integration by parts formula, we get the integral in as the product u times v, that's x to the n times e to the x, minus the integral over v du, where let's take the n outside as a factor. Now this is then the integral n times the integral of x to the n minus 1 e to the x dx, which one can rewrite as x to the n times e to the x minus n times the in minus 1 integral. That's the integral that involves the n minus 1 power of x. So we have found again the formula that expresses something that involves an nth power in terms of the same something, but then involving the n minus 1 power. And we can use this to calculate these integrals systematically. For example, the n equals 1 case is x times e to the x minus the I0 integral, which we already calculated here, and that gives x times e to the x minus e to the x plus c, which one can simplify to e to the x times x minus 1 plus c. Then the second integral, using the formula, I2 is x squared e to the x minus 2 times the I1 integral, which we just calculated. So this is x squared e to the x minus 2 times e to the x minus 1 plus c. And that, taking the e to the x out as a factor, can be simplified to e to the x times x squared minus 2x plus 2 plus c. And so on. I3 is x cubed times e to the x minus 3i2 from the formula that we computed here through integration by parts. And plugging the I2 into this formula gives x cubed e to the x minus 3 e to the x times x squared minus 2x plus 2 plus the constant c, which can be simplified taking the e to the x out as a common factor to e to the x times x cubed minus 3x squared plus 6x minus 6 plus c. And so on. I4 would be next, as far as you like. Now that's the reduction formulas as an application of integration by parts. So we've seen, after recalling that substitution reverses the chain rule, how integration by parts is an integration technique obtained from the product rule. And it can be expressed by this short formula, integral over u dv is equal to the product uv minus the integral over v du. In an application, we try and choose u and dv in such a way that the integral over v du is simpler than the original integral over u dv. We've seen how integration by parts also applies to definite integrals, and we've seen that sometimes it helps to apply it a couple of times. In particular, in the form of a reduction formula, integration by parts can be used to systematically reduce the power in an integral that involves the power of an expression. There's a few example exercises for you to go through, and that's it for now.